All right. Recorded. I'm starting recording. And all right. Well, welcome to class today. Got a few people missing. It looks like the day after Halloween, maybe. Yeah. All right. So if you look at the syllabus and compared it to what we're going to talk about today, you'll see that I didn't get up. Well, I'll explain it as I didn't get the lecture done for today. So that was it was a brand new one. What I did was I basically flip-flopped the next two. So this one was meant to be next week, but that's when we'll do the topic that I was meaning to introduce today. So today we'll talk about calibration, verification, validation, and then we'll do that lab. So let me go ahead and download this. And then I'm also going to download this this file called lecture10data.zip. One of the, I guess, advantages of doing this lecture first is that the lab for today, in the past, when I've told you to like make some output values and submit them with the results, we haven't really automated that process of making the output values in a format that is like in a table, in a neat format. And so today, maybe I'll talk about this more when we get to the lab. But today, what I want to do is spend a little bit more time on the lab explaining doing table manipulation so that we can get a formatted table that has the information we need to look up. So we can take that table and utilize it in a report or something. Okay. All right, so we're going to go over these three terms: calibration, verification, and validation. Specifically, how they relate to raster GIS data, which is the topic of the course.
Dr. Raper?
Yeah.
Real quick before you start, are you recording this particular lecture?
I am.
All right.
I hope it works. But I have uploaded the last couple weeks, and they seem to work. So I'm following the same process. All right. So one of the questions you could ask about a GIS or really any data product is it acceptable? Does it meet the needs that we want? More complete is the production of final output is at the end of the process, is that acceptable? If not, why? What needs to be done? So today we're going to talk about what things we need to do to be able to explain the results to the user, ensure its acceptability to the user, and then very importantly, determine its accuracy. So you can communicate that to the the stakeholders, the people that are interested in your results. So there are three different parts of accuracy here. call the first one calibration, and I'm sure there are other people who call them slightly different things, but lots of people in literature refer to this first aspect as calibration. Calibration is actually an exercise that you do when you're building a model to come up with accurate parameters to feed your model. Okay? So when we did things like the trek across Europe using the least cost path, I mean, to be honest, I kind of made up the values for how much it was going to cost in time to travel in various areas. Okay, but any model where we're doing something like that, how do we come up with the parameters that feed the model? And in a way, this is very similar to these other exercises, but we can't use the same set of data in order to do that. We need to calibrate our model and then verify its accuracy. So calibration is an exercise. We'll get into this further, but what are the parameter values in the model? Verification is the model producing the results that are expected? Verification and validation are both post-model things. The validation is what we often actually think of as accuracy. Is the model correct? The model producing results that are first, are they consistent with reality? And how do we measure if it's consistent with reality? Maybe they should be underneath that. What measurement is used to test for accuracy, and what statistic is used for the assessment? They're different. Depending on the type of data that we're getting, and the result that we're getting, there are different test statistics used to assess accuracy. Now, there are some other questions that could be asked, like, is the model acceptable to your clients? Acceptability doesn't always mean accuracy, is the point I'm trying to get across here, is that there are lots of other aspects of your model, like the precision, the time element, all those aspects need to be targeted to the people that are going to end up using the model. And a big part of that is being able to explain how the model works and what the scientific basis for the model is. Sometimes something that's performed is sensitivity analysis, looking at the model at different spatial scales or time scales. This is often a question that's asked in academic research, is to look at how sensitive a particular model is to changes in resolution or changes in time scale. And also, how different are the results going to be if any of the parameters are changed? All right, so we're going to first talk about calibration here. Calibration, and this is what we're going to do for the lab. We're going to do a calibration exercise. Okay? Determine what parameters will produce the results that you need, and what those parameter values need to be. Okay? So we're going to, in the lab, we're going to parameterize or calibrate a capability suitability model. That's what we're going to do. Okay? So our goal is to determine all the parameters in the model. This is something that we're actually going to cover a little bit later in the course. But one example would be to come up with a relationship, a linear relationship using mathematical regression. Here we've got, we could be trying to predict the temperature of a certain place based on elevation and latitude. That's a pretty basic example. And there's lots of other factors. So geographers out there, I guess there's only 5 of us here today, but what are some other factors that might affect temperature of, like, let's just say, average summertime temperature, besides elevation and latitude? Cloud cover, yeah. And what affects, what's a big driver for cloud cover? I mean, obviously moisture, right? So, so prevailing wind patterns and proximity to water, particularly warm water versus cold water, is going to produce different climates. So, different average summertime temperatures. But anyway, there are lots of mathematical models that are built using some sort of regression equation. In other words, a math problem that says that, in this case, in this example, temperature is a function of elevation and latitude. In reality, it's more complex. Okay? Runoff is a function of slope and soil type and, land cover, the surface characteristics, whether or not it's paved or it's a forest or whatnot. So when we have a model like this, and we'll cover this later in the course, I think it's like the second to last lecture, we would calibrate this using statistical analysis. In other words, there are plenty of software programs out there that allow you to feed them dependent variables and get a regression equation. In other words, a mathematical equation. All that they require is for you to have some empirical examples. In other words, that you have the values for both the predictors, which in this case would be elevation and latitude, and the predicted value, temperature, at that same place. So if this is a raster data set, we could get this data by extracting values at known locations. So if we had places where we knew temperature, we could extract elevation and latitude, let's say, the latitude would be easy, from a different data set, and then feed them into a statistics program that would allow us to get a trend line, okay, or a trend curve if we wanted to use a multiple regression. Okay? And I know here one of the requirements for the undergraduate degree is that you take a statistics course, and we actually teach an in-house statistics course for the graduates here. That's on for next semester. All right, so I gave that example. Also an example of rainfall runoff, computing the quantity of water flowing out of a basin, and then sometimes if the particular question is not linear in nature, sometimes it's even more complex than just not being linear. It's actually dependent on multiple variables. Sometimes it requires some trial and error approach, and that's similar to what we're going to do today in today's lab. Here we're talking about reference data. So in this particular example that I gave here, where I talked about the linear regression model, the reference data is the known output data, the response variable. So in this case, it would be temperature values, the values that we're trying to predict. And they're based on field measurements. We use reference data to calibrate and validate models. So they're used in both the calibration, this is what I meant during the first slide, earlier, that reference data is used both in calibration and in validation. Sometimes we refer to it as ground truth, okay? But ground truth isn't always the best term. in the remote sensing literature, you often see referred to as in situ data, or data that's of a higher, basically you have a higher confidence in its accuracy. Because even if you were in the field looking at something and getting a measurement, you could make a mistake. It's possible. So anyway, ground truth represents some observations signifying reality in GIS. So land cover type, observed temperature, mean household income. These are all variables, and if we wanted to make one of these the output of our model, so like we created a GIS model. I tried to come up with some socioeconomic examples too here. We could try to predict mean household income based on some other variables. But we would have to, in order to calibrate and validate our model, we have to have some measurements in the field of actual household income or and the other variables that we're trying to use to predict mean household income. So ground truth. I say that it's not in use anymore, but people still use the term ground truth, but technically we should probably be using a different term there. Okay, I think I accidentally skipped a slide there. So verification is the process used to evaluate if the implemented model is performing as intended and consistently. So basically, verification is a process that you use to systematically determine if your model is doing what it's supposed to do. In order to verify that a model is doing that, you have to have an understanding of the GIS logic operators and what the expected results should be. Some examples of verification problems, okay, are things like this: truncation. So sometimes you may be doing a addition in raster GIS. You may be adding or subtracting or multiplying, you're doing some math. And when you add an integer grid to a floating point grid, by default, it will always truncate it. It'll turn, 1 plus 0.2 is going to equal 1 unless you know to put FLOT, float, around the grid that's an integer grid. And so most of these verification processes are just going through and determining, looking at each output. So this process of building models in Model Builder, or later, if you take like a GIS programming course, the first thing to do with your model, even if it runs correctly, is to go through each step and verify that it's working and it's producing the results that it should be. That's why it's important to look at the result of two math operators and make sure that it's actually producing floating points and not integers. If you have a complex raster calculator expression, you need to look to make sure that you have the correct order of operations. So that involves being able to make sure and verify and understand what the raster calculator expression should be doing. One of the first things that I always look at when raster calculator expression isn't working is that the parentheses are in the right places. We all make mistakes. I make mistakes when you've seen it, when I type out these expressions. So getting those correct is important. All right. So conversion, constant mistakes. We forget to convert something. We've actually experienced this in this class with degrees to radians and radians to degrees. We've also got English to metric conversion. Dividing by 0, what to do with no data values. Something I just thought of was the extent being set correctly. ArcGIS tries to assume all sorts of things about the extent and the cell size that you want to use, which works well sometimes, but oftentimes when you're creating brand new data out of nothing, when you're making a new data set, like we've been doing in a number of the labs, the extent won't be very big. So if you don't go into environments and set the cell size, you won't get the results and the extent. You won't get the results that you need. All right, so kind of breaking this verification process down into its processes, you have to first select a small subset of the data that characterizes the problems. So this is really important because oftentimes your model it takes a long time to run. So sometimes, particularly when you get into actual real-world examples, I've made during our lab we've used kind of big cell sizes a lot of times, and that's so that it'll run faster. But when you go out into the workforce and you're attempting to operate on large data sets, if you don't do the verification on a small data set, it can take a really long time to do that. So subset out the data and try running it on a smaller area. And then work out manually what the results should be. Maybe for the steps of the process. So run the model and then compare the GIS model results that it computed by hand. Similar to like what I was trying to get across in the hydrology lab. We had a paper version of what was supposed to be done, and you were going to compare that to the result that ArcGIS put out, and it was a smaller area. It was a really, really tiny area, in fact. So, and then finally, we've got validation here. So, validation is the assessment of the performance of the model. So, the question, I should probably extend this. How well does the model work? And how do we measure how well the model works? Well, we have to compare it to some form of reality or some higher accuracy measurement. We may not have that everywhere. The purpose of the model is to be able to predict things that aren't necessarily known yet, right? But we have to at least find some smaller subset of reality where we do know the answer and see if the model works on that. So under what condition does the model fail? What does it produce good results? Those are good things to communicate and say, hey, this is my model. It works under these conditions. It doesn't work on other conditions. There are a bunch of statistical tests that allow us to basically compare the results of a model output to the results of to reality if we have some measurements. And we talked about a lot of these in those statistics courses. We're going to focus today mostly on this kappa, percent accuracy, and a measure that's similar to R-squared called RMSE to determine quantitative confidence in the output. R-squared we'll talk about specifically later when we get into regression in a couple of weeks. So to do validation, the first thing that you do would be to determine what reference data should be collected. Okay, then select a test statistic, collect the observations in the field, and conduct statistical evaluation. Now, you oftentimes will be needing to collect, as I mentioned several times now, in-field data for both calibration and validation. But you have to make sure that you use different data for calibration than you do for validation. Otherwise, your accuracy will always be high. In other words, you'll say, well, I use this data to calibrate the model, And then I used it to determine the accuracy of the model. Well, of course it's going to be high. It's like giving somebody the answers to the test before they take the test. Of course they're going to get the right answers. So typically, a best practice, I guess, is that you collect reference data, but you divide that up into two groups, one for modeling and the other for validation. Sometimes that saves money to do it at the same time, saves time. As we talked about kind of tangentially, but we did talk about this when we did the interpolation lecture, cross-validation is also a valid option. Okay, it requires, sometimes it requires a software tool or programming effort to do this, but cross-validation basically runs or calibrates the model a number of times and leaves one out each time it's calibrating the model, and then you can get an idea of how well overall it's doing because it's leaving one out to check. So you can calibrate the model 40 times and leave one example out each time and see how well that is working. So this is another verbal explanation of what's going on there. So one observation from the sample set is used for validation, and there's an iterative process. So you keep one out each time. And then you come up with an average error. Sometimes it's more than one. Like if you have 100, you could leave 5 or 10 out at a time. So these are two different forms of cross-validation. So one called bootstrapping. It's an iterative process. It allows for the replacement of sample data, and you can evaluate the variance of basically the sample data that's left out each time. There's an error associated with how far off the predicted value is from the actual value. And so you can come up with an average deviation or a variance from what the estimator was to the actual value. So Jackknife is basically a subset of this where we just leave one observation out at a time. All right. So we're gonna do some examples. Today, our lab example is going to be more of a discrete data example. So we're gonna talk a little bit now about a very basic method for calculating the accuracy in a digital elevation model. But this could represent any model that produced a numerical value. So if it produced a numerical raster, so if I was trying to predict temperature, precipitation, elevation, I was trying to predict income, and it was on a continuous scale, anything like that, I could use this test statistic to do that. So, but here's an example using elevation data. Typically, we want our reference data to be collected systematically. It doesn't say systematically. I mean, it does. Okay, systematically, preferably random, but oftentimes purely random points are harder to get. But that's the preferred method. And there are tools in ArcGIS to create a random set of points. So you can create a random set of points, go to those points, collect a value, and then you would have a result. So here's a elevation surface. We want to go take high high-grade measurements at each of these points. Okay, that's what those black points represent. Okay, this would be a very systematic approach, looking at a certain number of rows and columns. The only problem is if your the model has some sort of oscillation in the error, you're going to run the risk of the error being, like if this area is highly accurate, highly accurate, highly accurate, and the areas in between are inaccurate. If that happened, you would run the risk of finding only the areas that were either highly or highly inaccurate. Okay? Not a big probability of that happening, but it could happen. So this is a purely random sample. This is a clustered random sample, and this is often done in practice because it allows you to collect more points faster. So you can, if this was an area you had to drive to, you could drive to these areas and collect a number of random points. The last one here, I should put labels on each of these, but the last one is still random, but it ensures that there are a certain amount of points taken in different elevation areas. So in flat areas, there's a certain number of points. In steeply sloped areas, there's a certain number of points. So it's called a systematic random sample. So for this case, data set that is producing values on a continuous raster, like elevation and whatever we're trying to predict. One of the tools that's commonly used, or one of the statistics that's commonly used to assess accuracy, is called RMSE, or root mean squared error. So we're going to walk through creating this for a digital elevation model right here in Mississippi. Then we'll talk a little bit about this. We're kind of going to do this for the lab, but it's going to be really simple in our lab because in our lab we're basically just going to have, is it accurate or not accurate? But you can imagine a map that was like land cover, and you could have, it could be accurate or not accurate, but you might also be interested in knowing if it was biased toward any of the, let's say 10, 15 different land cover values. Okay. So here's the equation for root mean squared error. It might look like it's complex, but it's really pretty easy. So we'll talk about the other one in a second here. So I'm gonna open up. I don't know if I need that. So I'm gonna open up another version of ArcMap. That was from that was me developing the lab that I was going to do today. So I'm going to leave it up for a second. All right, and then I forgot whether I downloaded the data. Yep, I did. So you're welcome to follow along, but this is more of an example. We're not going to do the lab. I'm not going to build a model or anything. Although you'll be able to see that you could build a model for this sort of thing. I'm just going to put this right in CTemp. Wait for this to open. So the data that's in here is a digital elevation model of South Mississippi that we were trying to determine. We're trying to come up with an estimate of the accuracy for this digital elevation model. And the way that the digital elevation model was created was through interpolation. So interpolation itself is a model. And so we're empirically trying to find the accuracy of the model. instance, ctemp, lab 10. Initially, I had the original LiDAR postings included in the data, but it was too big. Okay? I actually tried to upload it this morning, and I noticed just before I got to class that it didn't upload, so I took the points out. So there was a data set that just showed all of the points that initially went into creating this digital elevation model. So today we're going to talk about some of the tools that are often used to assess the accuracy of a data set, particularly a raster data set. So oftentimes you have your ground truth or your in situ data. In this case, these dots, I'm going to change the colors here. These dots represent the default circle either. That's not blue. And that's too big. Whoops, go the wrong way. Okay. These blue dots represent areas where we actually took out the Trimble that's downstairs at Frank's office. It's supposed to get within 2 centimeters. Post-process, took the Trimble out, we surveyed in these locations. And this was a modified random sample. We actually randomly generated the points, but sometimes we weren't able to get to them. So we went to the closest area that we could get to legally. Most of these are kind of close to roads. Sometimes if we talk to the landowner, we got better data. So anyway, each of these points represents a survey grade GPS location. And we can actually right click and see the value. So here are the values right here. Under survey, I just called the field survey. Those are the elevations, the Z, and then the X and Y is stored as in the point itself. These are the X, Y, and Z locations for each of these little blue dots. And then the raster is an elevation data set that was created by interpolation. Now this could represent this could represent income or any other value. It could represent some pollutant. And we could be going out and taking the measurement at that location. All right? We actually did this, did something like that in the lab, right? Where we made in the interpolation lab, we used the zinc or magnesium or whatever. So it wasn't elevation that was being predicted. So imagine if this is that other data set, or whatever data set this is, we're going to try to come up with the statistic that tells us how close we are to the reality at these locations. It's basically just like we're taking the average error. So the first step that we're going to do is calculate that, the error or the deviations. That's this. So we have a bunch of points. Now we're looking at a side view. We have a bunch of points, and we want to find the deviation from the surface, from the in this case the digital elevation model, from the raster. Right? So there's a tool that is used to do this a lot, and it works for categorical variables or continuous variables like we're doing here. That's under spatial analysis, and it's under extraction. And there's a bunch of different extractions, but extract values to points is the tool that's very useful for this. If you have multiple rasters, you can use extract values to points, and it will extract values from a series of rasters. Let's click this one for a second. So you can input like 10 rasters, and it will extract all the values if you're trying to come up with the accuracy for multiple rasters. We're just doing it to our one raster right here. So we're going to go extract values to points. And it's a pretty simple tool. All it does is it takes your point features and it takes a raster, and what it's going to do is append another attribute onto your point features that tell you the value of the raster at that location. Now there's only a few other, well, there's obviously the output. I'm going to save the output here before I talk about the rest. So let's talk, where I put this, C, temp. Data, survey with output. Or I'm going to say with DEM values, with DEM. I'll just say with DEM. All right, there's a couple of options here. One is to interpolate the values at the point locations, and that's optional. What this does is that, I mean, obviously, when I went out there with the Trimble GPS measurement, it would have taken me forever to ensure that each dot was taken at the center of the cell. It's hard to see on this, but you can see it if you go back and watch the video later. Maybe if I change the colors here, symbology. Not really, but you can see this is a cell, and this dot isn't on the center of the cell, and there's no way it should be. I mean, that would be really, really hard to make sure that all the dots were at the center of the cells. So what this option is doing is saying, if your values are not in the center of the cell, do you want me to come up with an average value that it should be based on all the surrounding cells? So that's kind of up to you to decide what's accurate and what's not accurate. Personally, I think that when we're dealing with something like elevation, that's probably a good thing to do, because where I collected the value, it might be more of an average between the two neighboring cells, and I'm more comfortable reporting that as the accuracy than I am saying that it should be the value at the center of the cell that I'm in. And there's no hard and fast rule here, so maybe if the cells were really, really tiny, there wouldn't be a reason to do that. If the cells are really, really big, there may be even more of a reason to do that. Okay? And also, what variable I'm mapping may have an influence there. So that's what that does anyway. I'm giving you an explanation. Feel free to think about that, to think on that more. All right. Now, if it's a categorical variable, in other words, if it's something like land cover, and you're extracting all of the land cover values, you don't want to interpolate, because the land cover values, you know, if one is 14 and the other is 1 right next door, okay, 14 means something like maybe sidewalk or road, and 1 might mean open field. And so if you click to interpolate, and it comes up with a value of 7, which means forest, that's silly. Do you see what I'm saying? You can only use interpolation if you're actually using numbers. So if the numbers in your raster don't mean numerical values, you definitely wouldn't click this. You're only going to click. That's why that option exists. You're only going to click this if you're using numbers. Okay. Also, using categorical values, your raster will oftentimes have a raster attribute table. Let's see if I can go to my other ArcGIS. Okay, so this is an example of a data set. Let me just turn this one off. You don't have this, but I'm going to show this real quick. This is the Laguna Beach area that we've been working with in other labs. What isn't that? So this land cover data set, this is an example. Huh. Let me just, oh, maybe it doesn't exist here. Zoom to layer. Some of these other data sets are showing up. Oh, you know what it is? I was working from my thumb drive. Let me see if this will work now. Oh. Okay. I guess you can't unplug and replug in and expect it to work. Try one more time. Nope. Zoom to layer. Well, anyway, I'll open up the raster attribute table. So this is a raster, and these are land cover types. Okay? So you've all probably worked with rasters like this. It's not a raster that represents that has numerical values that represent some quantity. And so this raster attribute table will exist for categorical values. And you can actually add fields just like with the feature class table. You can add fields, and right now it's not loading, but these values right here, class, developed, high, medium, they appear in this column. In fact, they're what I used to make this legend. And that's why they appear there. Okay. So if you clicked this, it would add all of those rows in the attribute table into your result. So this doesn't really make sense to us because we don't even have an attribute table in the DEM. But if we were doing something like land cover, it might be important because then you get the class name and not just the value of the raster. So I'm going to hit OK here. It's going to run through, and it shouldn't take too long. See if this decided to draw yet. I wonder what you have to do to tell it. I'm going to save it. Okay, it finished. Now, like with most other tools, it doesn't modify your data in place, which in this particular case, sometimes I'm like, why not? It's just putting another field on it. But it doesn't. It creates a whole another data set. And so in your new data set, if you right-click on it and open the attribute table, now, for each of those points, you have a new field called raster value without an E. That's just the way ArcGIS codes it. So we have a field called survey and a field called raster value. And I've already done this exercise, so it's not like a relief to me. But when I first do this, it's a relief to me because I can see that those values are fairly close. You know, they're within a little bit. So I know that I don't have any projection problems and that my data set is producing the values that I want. I could take this right into like Excel or if I wanted to, some more fancy statistics program and actually plot the known values to the unknown values and see if there was like a trend, are there some areas where they're off by a whole lot and some areas where they're better by just taking those two. In fact, if I just take this file and let's say I export it to a DBF, I'm going to put it C10 Vector 10 data. It's been open for a little while there. Open this PC. I really don't like. I like being able to look at the data itself. I mean the folder structure itself. Vector 10 data. How come that didn't? Can I not open a DBF table anymore? This PC. No. Temp and then lecture. Star. Try to open up the DBF and see if it works. Yep. Okay. So I can highlight those two columns and then insert a scatter plot. Wow, those are pretty tight. I didn't remember. Usually I don't make a scatter plot of this data, but not every time you do this exercise. Like if we were trying to predict one of those things from the interpolation lab, we might get more of a scatter here. Okay? And we could like find out which ones were further off and see if they were the ones that were kind of on the edge or if they were associated with something else. But these are pretty tight. It looks like there's almost a one-to-one relationship in terms of the error. They're not like all. I'd be worried if like they were all, let's say, off by exactly a meter or something. That just would mean that my GPS was probably off by a certain amount, or one of the data sets was off by something. If we already said and trend line, right? Set intercept display equation. Yeah, so that doesn't really help us here, but you could use that information. So basically, what this is saying is that y is equal to 0.99999 times x. So really, they're almost the same. But in an elevation data set that should be within 2 centimeters, you would expect it to be really tight like that. Okay, but if we were doing some other model where we were trying to predict something that was harder to predict, like income, it would be interesting to look at this one. I didn't expect to show the Excel graph there, so I didn't realize it would be as uninteresting for that one. Okay, back to predicting an RMSE value. Okay, so an RMSE value will tell us in these units, so that later when we talk about regression, okay, this number right here, this R squared, kind of explains how well those two data sets, how well one per data set predicts the other. Okay, this is the square of the correlation coefficient. The only problem with this is it expresses it on a scale from 0 to 1. Okay, and that's great for saying, well, it's a really strong relationship or it's a weak relationship. Okay, but And that's one thing to report. But what I wanted to focus on today is this RMSE, because the units are going to be in the same units. So we'll be able to come up with a way to express the average difference somebody should expect to see in the raster. So if I'm at any particular location on the map, I'm going to come up with a number that says, yeah, well, we could be anywhere within this particular range. So the way to do that, well, they aren't correlation coefficients. They're not. But they're a measure of accuracy. So they're in the same units as your map. So in our case, our map's in feet above sea level. If we're measuring something like income or zinc pollution, then it would be in whatever units we measured the zinc pollution or the. So the correlation coefficient, which we'll talk about later, measures how measures how close your measurements are to reality, how well they fit, because sometimes they're like way off. It's more of it's a measure of predictive capability. RMSE is map accuracy. It's a way to express how confident you are in any particular measurement. So you could say, this is a measurement of how far off we're going to be in a location. Okay. Well, it's one of the steps in creating a confidence interval. Yeah. And we can demonstrate that. Okay, so the next thing I'm going to do is add a new field. A new field, and I'm going to call that new field, I'm going to make it a double. I always love saying that because it sounds like I'm ordering something. All right, I'm going to make it a double. The reason I'm making it a double is it stands for double precision floating point number. And I'm going to call this squared. Actually, I'm just going to call it error at first, okay? So the error is the difference between the known value and the measured value. So this is the measured value, the raster value. The survey is the known value, or the ground truth, or the in situ measurement, the one that I'm saying is more accurate. So to calculate the error, I can use field calculator and simply do a subtraction problem. Okay? Now, to calculate RMSE, it doesn't matter which order you do it in, because eventually we're going to square the number and everything's going to be positive. However, if you're just calculating raw error, I think that it makes the most sense to make it so that measurements below the surface show up as negative and measurements above the surface show up as positive. Okay? So below the surface, negative. So how would we do that? Well, we need to make sure that, let's just put it in. If we put in survey minus raster value, okay, the survey measurement, if the survey measurement is bigger than the raster value, it's going to be positive. That's right? If the survey value is smaller than the raster value, it's going to be negative. So that's the right way to do it, because that means that the survey is below the surface if it winds up negative. So survey minus raster value. Now, so far, we've ran the extract values to points tool, and now we've run field calculator. Those are both tools that we could get in the toolbox. I ran field calculator different, but today during the lab, we're going to use the calculate field tool. So we're going to get a little closer. Okay, so we can see now that here's the error, and we can see in some some areas, the error is pretty low, like right here. Okay, we're only off by 4 hundredths of a foot. These are in feet, sorry. I didn't use metric. But here we're off by over a foot. Okay? So even though our measurement is highly accurate, we're still off by over a foot. So that tells us something about our method, is that we're off by something. So like I said, if all of these measurements were equally off, that would be worrisome, because that just means that there's some bias in one of the tools that we used, whether it was the survey instrument or the interpolation process. But these seem pretty random, okay, which is good, because when the errors are random like this, we can have a little more confidence that our RMSE value means what we think it means. All right, so sometimes I just create squared error, but this time what I'm going to do is create another field called, I'm going to create another field, I'm going to add another field and call this squared error. This is also going to be a double. And I'm going to calculate a field, and that field is going to be called, that field is just going to be error times error. So it's the squared error, because RMSE actually stands for root mean squared error. Say OK here. Now I've got all these squared errors. So here we're adding up all of the squared errors. That's what the summation sign means. So we've got all our squared errors, and you'll notice. Look at the line that I've highlighted right here, the top one. So when the error was a half of a foot, 0.52 feet, the squared error is actually 0.27 feet. Interesting. So, and that is the case. When you square something that is less than 1, it actually get closer to 0. When you square something that is greater than 1, it gets bigger than 1 in an exponential way. So we've got 1.21 becomes 1.469. Okay. So to get root mean squared error, we just go to the squared error, right click, and say summarize. No, not summarize. Statistics. And it'll give us the mean. There's the mean right there. The mean is 0.36745. That's the average error. The average squared error, sorry. The last thing that we need to do is take the square root of that. That's this part. So we did everything below the square root sign. And then we could just go like this. Square root of 0.606. So you notice that went back out, because when we squared it, it's like the opposite of numbers above 1. So the result here is that the RMSE is 0.606, so about 0.61 of a foot. About a third of a foot is the error. Okay? So we know that the instrument itself is reported about a third of a centimeter, or sorry, 2/3 of, that is 2/3. So about 2/3 of a foot. We know that the accuracy of the instrument is about 2/3 of an inch. And so the rest of that, the rest of that error is just associated with the interpolation technique and the data collection. So we have the ability to say that on average, because we randomly sampled this thing, that the error is on the order of about 1/3 of a foot. Okay? Now there are different ways to actually report your measurement to your user. I was gonna add these into the slides, but I didn't. Okay. I might not. I should have put these in the lectures. There is a set multiplier, 1 point something. There we go. Nope. Anyway, maybe I'll find this during the break. But your RMSE, that was specifically from an organization that is looking at elevation data. But in any case, when you report this kind of average error, okay, the RMSE statistic. Well, let's just say that I calculated. Does anybody know what the concept of standard deviation? Let's say I got everybody's heights in here. I calculated the mean, and then I calculated the standard deviation. Would everybody's height fall within the standard deviation? No, right? If you take a statistics course, most of the time, if it's heights are normally distributed. If heights are normally distributed, most of the time, about 60-something% of the people's heights will fall within one standard deviation. Well, if you look at the formula for standard deviation, it's actually really, really similar to this formula, except it uses the mean instead of the real x. Okay? Very, very similar formula. Used in a very, very similar way. So instead of using real x, it uses the mean. But with data, it makes more sense to use the real x. That's kind of like the mean, the true value here. And so what we're saying is that the real value will fall about 60-something% of the time within one RMSE unit away from the mean. Okay? So just like with standard deviation, you multiply it by like 1.96 to get all the way out to 3 standard deviations away from the mean. So when they use this to report as a map accuracy standard, we would multiply 0.6. We would multiply that value we got 0.60 by 1.96, and we could be fairly confident almost all of the values. And the only assumption that we're making is that these errors are normally distributed. These are the errors that we collected. Do they look normal? Not completely normal, right? There is a kind of a peak in the middle, but then there's this little thing. It'd be interesting to look and see if it looked more normal using a different number of bins. Like if we only use half the number of bins there, it would probably have a high peak in the middle. Anyway, it is. I would say it is close to normal and close enough to because these predictors are robust. It's close enough to be able to use that value. If you do notice that your errors are not normally distributed, it's oftentimes because your measurement, there's something wrong with the way you're measuring the values, because your errors should be, close to the mean. Okay. All right, so that's root mean squared error. All right. Now, I didn't prepare an example for this. I probably should now. I used to do this as part of our 315 class. So that's one reason why I didn't prepare an example there. But let's say we had two different land cover data sets, and we wanted to compare. We had one. We have one land cover data set, and we go out and we find points, and we write down what the real land cover is at those points. We could use extract values to points to get the actual land cover and the land cover that we modeled into the same data set. So we have a row that represented actual land cover and a row that represented modeled land cover from a remotely sensed data set. And then we could create a confusion matrix like this. Right? So I don't have this as part of an exercise, but what I did do is I found somebody who did a really good job doing this in ArcGIS already, and he made a video. So you can watch this video. But basically, the tool involves running first extract values to points, then running another tool called pivot table. And what pivot table does is it lets you take two columns, and with those two columns, it basically creates something like this, where it says, okay, these are all the different values you had in each of those columns. I'm going to count up those values. I'll show you, I can show you where that is. So it's not strictly a raster I hate how it doesn't show me the first sort by type. No. Date. Trying to get it to let me get that. It's not gonna let me choose it. Where is it in? System toolboxes, data management. So there we go. System toolboxes, data management, table. It's in here under table. So you could. Oh, sorry. Yeah, I sometimes I forget to stop the. You have to stop the slideshow, otherwise that keeps showing up. Okay, so this is the tool right here. It's under data management tools, table, and then pivot table. And so what it does is you can actually do it with multiple fields, but typically what you do is you have one of your fields here. And then your other field, your output table. This video does a good job explaining how you run the tool and what creates the pivot table. Why doesn't it let me click on that? I do have an exercise that I used to run as part of 315. I can also put up. I wonder what's on. Hot. Let me hit that hot link. Oh, there we go. What's that? It was. I haven't done it. I didn't do it last time. I did drones last time, but yeah. See, this is. Made the same mistake. So this is an example of the data that they get from the pivot table. The diagonals are always the ones that are correct. In other words, there's C in the ground truth. He's using the term ground truth, which I said you should use a different term, but he's using the term ground truth. So the sea ice is sea ice. Okay? Water is water. This just has two categories. In fact, this is going to be really close to what we're going to do. So we're going to do it in a different way in the lab today. But he's running it using the pivot table. And then later he does another example where he looks at, so see how he ran extract values to points. He does another example with land cover. Right here, here's the land cover example. And he even talks about running that random tool to create the random locations. So it's a good video to watch. All right, so what we're going to do is do some calibration of a capability suitability model for the lab. And in order to do that, we're going to do lots of table manipulation. Like I said, we kind of left that out. But let's go ahead and take our 15-minute break. So we'll come back at 2:40, and I'll restart the video then, so that we'll make sure that I like to split them up, the videos up, so that they are easier to manage and to make sure that, you know, if one fails, at least they don't both fail.